In our last video about gas laws, we talked about Boyle's law, which involves pressure and volume. In this case, we're going to look at Charles' law, and this is with volume and temperature. So I have two pictures here to demonstrate what I'm going to explain. The picture on the left is actually my mom and I as we are working with hot air balloons. Notice on the left-hand side you have a fan that is blowing air into that balloon. So we're filling that balloon with some initial volume of air. And of course that volume that we're pushing in, it's going to be relatively cold. Notice we're all bundled up in jackets. It's just pulling air out of the atmosphere and pushing that cold air into the balloon. So on the right-hand side, after it's filled with enough air to get you started, you will start to increase the temperature by blowing a flame directly into that balloon. You can also see that that balloon is starting to lift off of the ground, which tells us that the volume has gotten even greater. It has increased. So on the left, we can say that the temperature is relatively low, and the volume is also relatively low. And then on the right, as we increase that temperature by adding that heat, we are also increasing the volume. So notice as temperature goes up, volume also goes up, or as temperature goes down, volume will also go down. So we will say that temperature and volume are directly proportional. Because of that, we can write an equation, and Charles' law is represented by this equation right here. V1 over T1, or volume over temperature of the first one, is equal to V2 over T2. I should also point out that T, or that temperature, is measured in kelvins. So Kelvin, it's represented by that capital K, is the degrees in Celsius plus 273. So let's look at an example problem. If we say that a balloon takes up 625 liters at 0 degrees Celsius, and then we heat it to 80 degrees Celsius, what is that new volume going to be? So just like in our previous video with Boyle's law, I went ahead and pulled out our variables. So V1 was given to us, T1 was given to us, but notice that that temperature was given in Celsius. So I added that 0 plus 273 to get kelvins, which is 273 kelvins. And then V2 is what we're solving for. In the second temperature, which was also given in Celsius, I've done 80 plus 273 to get our temperature, which is 353 kelvins. All right, so now we know we're solving for V2, or the second volume. I took our initial equation that we just talked about, so V1 over T1 is equal to V2 over T2. Multiply both sides by T2 to get that V2 by itself. Here's the equation I'm working with. That second volume is equal to V1 over T1 times T2. So we can plug in our values. Notice that the Kelvin will cancel out, and we're left with our units in liters. So this tells us that V2 is equal to 808 liters. So let's check our work. We said before that as temperature increases, the volume should also increase. Our temperature went from 273 kelvins to 353 kelvins. Our volume went from 625 liters to 808 liters. So that checks out. It follows what we predicted, and that is the correct